Good afternoon. This is Chris Kenberg from IFG, and this is part two of topic three. It's the rise of digital machines. It's just a little exploration into the nature of digital machines, together with ways of actually specifying such machines, and some hint and detail about their implementation in both software and hardware. So I hope you find this quite interesting. So the purpose of this talk is to introduce you to the idea of a finite state machine by means of which we can describe a most interesting class of machines. I mean, I hazard a guess to say that most of the machines that you will be able to identify in day-to-day life will be of the form of a finite state machine. And I'll explain what I mean by a finite state machine in some detail in what follows. Um, the word finite simply indicates that we're not talking about a system with an infinite number of states, but simply a finite state machine. I mean, the finite number of states might be very, very large. For example, a laptop is a system that might well be capable of being in any one of, say, 200,000 different states. And I'm going to try and explain what I mean by a state machine in a few moments. So, a characterization of machines in general is that a machine is actually anything that has behavior that can be characterized by what's observable in terms of inputs and outputs, just as humans can be identified more or less in terms of the kind of person they are, in terms of uh, if you present a particular input to a human, then that human, more likely than not, is going to respond by um, outputting a set of behavioural traits and so on. But I'll clarify what I mean by that in a few moments. So, in this context, what's observable is its input-output characteristics. For example, if an input in occurs, then an output out occurs. And simple illustration of a simple machine is a light switch. I mean, it's probably the simplest two-state, finite state machine I can think of. So, if I flick a light switch, uh, maybe a light comes on. Flick it again, and if the previous state was being on, the next state goes off. It's the off state. Click it again, and of course it goes on again if it's functioning correctly. So, what I want you to notice from this very simple illustration of a finite state machine is simply um, the output depends on what state it is in when it's the switch is toggled the other way, whether it's on or off. In other words, if it's in state on, then you flick the switch and it goes off, and vice versa. And that's the key thing. The next state that a system is going to be in typically will depend on its previous state. What state it was in before a set of inputs or uh, arrives and causes a change in state and maybe a change in output as well. We're not actually interested at the moment how the machine is implemented, how it's built or constructed. It's of no relevance at the moment whether it be built-in hardware or software or even wetware or some other particular medium capable of implementing a digital system. I mean, you may have seen the film called Solaris, um, who, the author of which was Alexander Lem, a Polish gentleman, and it's a film in which one of the spacemen featured falls in love with an unstable neutrino system, and it turns out she was indiscernible or indistinguishable from a real human being because you could talk to her, she'd move, she'd pick things up, she could ask you questions, she could enjoy your sense of humour, and so on and so on and so on. I mean, the only discernible difference between this lady and uh, a real lady was that she would suddenly pop into and out of existence. I mean, it's quite dramatic, and it's quite a good film. And a bit of a problem if the woman you love actually doesn't have a continuous existence. And I mentioned the Turing test, so I'd like you to find out by looking up on Google, what the Turing test actually means, and perhaps you'll become interested in that. It simply says something to the effect that if there's nothing you can do, no test you can perform to bring about a distinction between a real object and an imitation object, then the two are the same. Well, bit more precisely, if an object X has all the characteristics of a particular person I know. In other words, you can ask it questions, it can give you very sensible, coherent answers back. You wouldn't know the difference between its being a machine and being a human in certain respects. And you can treat the machine as exactly the same way that you treat a person. So it's quite interesting, quite an interesting area to explore. So what I've given you here are three references to vending machine examples of finite state machines. These examples represent a bit more complexity than a light switch. So have a look at them and have a little bit of a think about what's going on. And um, so machine types, I want to discuss different sorts of machine. The kind of machine we're looking at is history dependent. In other words, what output or what state they change to given a particular state in part depends on the history of the states that they have been in, and in particular the current state. And this together with its current inputs determines the next state and the next output that the machine is going to give. So in other words, the behaviour of these sorts of machines depends on two things: state and current inputs. What is their current state? What are their current inputs? These two elements will actually go to determine the next state and the next input. You can calculate by logic alone what the next state is going to be. I think you will already be able to give many examples of such simple machines. And what's interesting are what are called state machines. These are machines that produce an output in response not only to an input but to the machine's current state. And I've just said that. Though these can be compared to systems which are made out of, say, single layers of logic gates, ands and ors, and maybe ifs and thens. And because those systems, by definition, do not have state, and I'll talk to you a little bit about how a machine comes to have state, and what a system looks like when it doesn't have state. Right. So you might want to consider that a human behaves in many respects like a state machine. I mean, maybe the states that a human being can be in far exceeds the states that a laptop could be in. And as we've seen, a laptop can be in an enormous number of different states. But I'm thinking in terms of Maybe when you were 10 years old, you went through a series of states that changed. As you grew up and you matured, you could do different things, different abilities. You had a different range of emotions and different desires and different ambitions, and you're capable of being in lots of different states. But anyway, that's a matter of debate, and it's a bit controversial to liken a human being to a state machine. Um, for example, if I have a headache and you ask me a rather silly question, I might respond to you rather grumpily and say, look, just don't bother me. If I'm hungry, I'm in a state of being hungry, and you give me a biscuit, I'll eat it, but if I'm not hungry, I will ignore it. Okay? I mean, you can multiply the number of examples indefinitely. Consider a vending machine, a machine that sells chocolate in response to your insertion of money. If it's ready to sell goods, I mean, if it's got a stock of chocolate inside and it's been, um, it's been powered up and so on, then if I insert a pound coin and then press the Choco button, so the machine will dispense a bar of chocolate if its cost is precisely that amount. Maybe if I insert a £2 coin, then press the Choco button, not only does the machine respond with the chocolate, but it gives me some change. Now, the right change, hopefully. But if I insert a coin and do nothing else will happen. I mean, if I don't make a choice, uh, at best the machine might say after 5 minutes, hey, you've put some money in, but you haven't made a choice. If I insert a 50p piece and press the Choco button, the machine might say to me, you haven't inserted enough money, try again, put some more money in. And you get the idea. So hopefully the idea of a machine that will respond to a particular input or inputs whilst in a particular state makes clear sense, and maybe it will respond differently if it's presently in some other state. And hopefully the idea of a machine being in different states also makes sense. Intuitively, it makes a bit of sense to me. Another example. Okay, well, I'll mention one other example. Machines can change the state they are in according to their current state and new input. For example, if a vending machine is in state A and it receives a pound coin, then it will enter a new state, which is a state in which it can accept a choice button being pressed. And if a choice button is pressed, it might ask you for the right amount of money to pay for it. So in state C, it might then say, look, client, you've made a choice, you want some chocolate, put the money in. Or it might be the other way around. First of all, it asks you to part with some of your cash and then make a choice. And the choice might actually be between a bar of chocolate and a cup of tea. It wouldn't. It wouldn't. I don't know how. It wouldn't accept a choice button being pressed if it had been in state A, but it might have warned the user that no money had yet been inserted. So you get the idea. And here's a very, very simple example that I want you to think uh, very carefully about and do your best to come to understand this. So it's a very simple machine. As you can see, it's got exactly two inputs and digital inputs. So the input, you can put either a 0 or a 1. And on the G input, you can either put a 1 or a 0. And in response to whatever state this little machine is in, it'll produce an output. But the output will depend on two things, namely the input, the data input, And this signal here, as we'll see, and the particular state that the system's in. So very simple, two inputs in and G and a single output out. So there are in fact two general sorts of machine for our working purposes. Type 1 is a machine that will determine its next state on the basis of current state and current inputs. And its outputs are completely determined by the new state, by the state that it changes into. So, putting it another way, if you've got a Moore machine, this is called a Moore machine, name of a of extremely well-known scientist. If you uh, uh, if you uh, give the machine an input, then depending on which state it's in, it will change state and give you an output. And I haven't mentioned the G input, the second input, but I'll speak about that in a moment. Right. Type 2 machine. This machine will determine its next state from current state and inputs as before, but its outputs will be determined by the new state and the current inputs. So in other words, um, uh, a Moore machine, when it changes state, it's going to have a unique output. A Mealy machine, however, when it changes state, is going to change state according to current state and current inputs, but its output is going to be dependent on its current state, the new current state, and the current inputs. So in other words, if you think about it, the output in a given Mealy machine state uh, is not unique. There can be any number of different outputs. So that might seem a bit strange, but we'll think about that a bit later on. So here's a horrible looking diagram, but it's actually very simple, and it sums a fair amount up. This is a generic Moore machine, and what it shows is several incoming inputs, and it shows what goes into this block of logic is a set of digital inputs, like a bus almost, which represents the current state. The current state. Okay, so what this block does, and here for some reason I've called it transition logic, or otherwise it's a better name for it is probably next state logic. What this logic block does is to look at the current state, look at the current inputs, and it outputs the new the next state, which is captured in this little block of memory. I mean, if it's a simple machine, memory will consist of just one bit of information to represent the two states that the machine can be in. If it's a slightly more complicated machine, state memory needs 4 bits of information, and so on and so on and so on. And the output is the new current state, which is being fed back into the system. So let's go through that again. Next state logic will, on the basis of current state, i.e. the state that's being remembered by this block of memory, and the current inputs, and T actually calculates what the next state is, and it changes, it forces the state to be changed. And after it has done that, then the new state is going to be fed back. So it's a Moore machine, so what we do, what I said earlier in the case of a Moore machine, is that the state that the machine's in actually determines its output uniquely. There's only one output per state. So hopefully you'll start to think about a Moore machine and try and get to understand it. But it's a little bit tricky because you're talking about, in principle, a machine whose output is determined by two things. It's what state it's in at the moment and the current inputs. So I want to characterize our little blue machine that I showed you in the slide above. And you can define a machine's behavior precisely by describing its input or output behavior. There's nothing more to the machine than what it does in response to the inputs it receives. And you might think that's a bit strange and a bit outrageous or a bit, nothing more than the machine's behavior. I mean, as long as a system behaves in such and such a way, that is the machine. I mean, it doesn't matter whether I've made it out of mechanical parts or electronic components or plant material or whether it's part of a monkey's brain. Right, that's my definition of a machine's behavior. All you need to know about is its input-output behavior over time. Right? So firstly, for the machine above, I'm going to say if G is 0, then the output is whatever it was before G became 0. Okay, so look at that. Where asterisk is the value that input in had immediately before G became 0. In other words, its past state. It'll continue outputting its past state. Whatever state it was in before, it's going to continue to output. And at this point, I invite you to think of G standing for the gate. And I can reread this line as saying, if the gate shuts and closes, then I'm going to continue outputting whatever I was outputting beforehand. All right? But if the input is 0 and the gate is 1, in other words, the gate is open, wide open, then the output is going to be the reflection of the input. So if the input in is 0 and the gate's open, then the output is also 0. And likewise, if the input is 1, logic 1, and the gate is open, then output is going to reflect whatever is on the input, namely 1. Okay, so it's a pretty simple machine. But on the other hand, if you think about it, let's just revisit our little machine. So if you think about it, if the gate's open, then whatever I put on the input is going to be stored. It's going to be stored on output. Outputs will be the value of the input when the gate closes. When it's open, if I change in from 1 to 0, I'm going to get an output changing from 1 to 0 whilst the gate is open. If the gate now closes, then whatever was on the input, let's supposing it is 1, is going to stay on the output. In other words, what we've actually specified is a one-digit memory, one binary digit memory. It's a little unit that can actually remember a 1 or a 0. And if I've got 1,000 of these, well, my little system can remember 1,000 bits of information. And maybe it can actually remember a telephone number, which is good, and it'll remember that for all time. For as long as the system doesn't deteriorate, as long as the system uh, retains its integrity. So we've looked at Moore and Mealy machine. We've looked at a generic Moore machine. We've described a simple um, machine, two states. What are the states? 0 and 1. The system can't be in any other state. It's 1 or a 0. And in what follows, I'm introducing you to some notation which enables us to represent uh, our little experimental digital systems very easily. And the notation, the symbolism, just involves a circle which represents a state, an arrow. So we've only got two things: arrows, two arrows here, and a circle representing a state. And what I write in the circle is the output given when the system's in this particular state, which I've labelled state 0. So what I've decorated the this arrow, which goes back on itself. So it says stay in this state. The meaning of this arrow means stay in this state for these input conditions, for whatever they are. Maybe it's just for in the input in to be 1. Stay in this state. And on the other hand, so supposing in 0 is going to make the system stay in this state, but if the input 0 changes from 0 to 1, maybe I want the system to change state. And I can write that simply by an outgoing arrow, and maybe I'm changing state, so I'm going to write another circle here, and that'll represent the state that I'm now in after moving from state O here. So circles represent states, arrows represent transitions, changes between states. And what I can actually represent, believe it or not, is to represent all the information I've got here written in English language. I've described the behavior of a machine, but I prefer to represent all that information in a diagram like this. I've got two states, state A and state B. And in state A, let's have a look at this together. We're outputting a 1, and whilst the two inputs, G and N, are both 1, I'm going to stay in that state and output a 1. Well, why? Do you remember me saying if the gate is open and the input is equal to 1, I'm going to output a 1. And I do that as long as that condition holds true. On the other hand, if the gate suddenly changes, it's shut, I'm still going to output a 1. Do you remember? The input was 1, the gate was open, but it now closes. G is 0. But I continue to output 1. So there's lots of other possibilities. Supposing the gate is 1 and the input changes from 1 here to 0. Well, I'm actually going to change state, and what the specification above tells me is that if the gate's open but the input changes to 0, output a 0. Output a 0. And on the other hand, if the gate stays open but then the input changes from 0 to 1, I go back to this state, state A, and output a 1. If I'm in state B, which is it's a state in which I'm outputting a 0, if a gate is 1, gate's open, and input stays at 0, I'm going to continue to stay in this state. I'm not going to move out of it. I'm not shooting off anywhere. I'm going to stay in this state and output a 0. And if the gate closes, because it's open here, I'm still going to output a 0. Because remember, what I'm designing here is a little memory. But logically, this is showing the behavior of this two-state machine. It's clearly showing two states. It's clearly telling you how it behaves if you change either or both of the inputs. So let's put all the information above into a diagram. This is what I get. I mean, you might think, oh, I've never seen a diagram like this. What on earth? But just follow it through in the way in which I've explained it, and try and convince yourself that what I'm actually describing by means of this finite state machine diagram is what I've actually described in words above. It's that of a very simple memory. So I might as well finish what I'm doing here, and I'm actually going to present you with two other things. So this is a representation of the system above. I mean, instead of a gate called G, I've got a pin on this little device called E, which stands for enable. If enable's 1, and that's the same as the gate being open, then my output Q is going to be 0 if the data is 0. If, on the other hand, enable becomes 0 and the data in is 1, I'm going to get a 1 here. And this is called a, well, perhaps truth table is not the right term for it. I'd call this some kind of excitation table. It tells you what, for these inputs, what the outputs are. And so if the gate or enable is 0, no matter what the value of D is, I'm going to get that value on Q. So it's the previous value of Q. Sorry, previous value of Q. Alright, so if the gate goes off, if E or G goes off, the value held here is going to stay here. Okay, the gate is shut. On the other hand, if the gate's open and D is 0, gate's open, I'm going to get a Q equal to 0 and not Q. Whoops, let me see. And not Q is going to be 1. Likewise, if the gate's open, right, there it is, gate's on, E is 1 and D is 1, then the output Q is going to be 1. So E, the gate is 1, D is 1, the output Q is 1, and not Q is going to be 0. Because this device, the device I'm currently looking at, has two outputs, Q and Q, what's called Q bar. It's not Q. So it's a bit like my English language description of the system, but I put it into what's called an excitation table or truth table here. So a little explanation here. And these waveforms give exactly the same information as this table here, but it's in a different format. So if D changes from 0 to 1, after enable goes to 0, I'm going to keep um, uh, the value. The output Q is going to stay at 1, at 1 here. So at this point, the gate is shut, and in fact I change D from 1 to 0. I'm going to still continue to output 1. If enable goes on and the data line becomes 1, then okay, the output Q is going to be 1 again. At this point, the gate goes off whilst D is 0. So at this point, the Q output is 0. Well, I'm going to let you look at this, and I want you to, if you've a bit of time, 10 minutes or so at some point in the next week, have a look at this table and just convince yourself that the behavior of this device is reflected in a different way, graphically speaking, by this diagram, which is called the waveforms of the four uh, two inputs and two outputs. So just think of this. E is 1 up to this point, then it closes. And it closes at this point in time where D is 1. So I'm going to output a 1 for all this duration. Convince yourself that this is valid. When the gate closes at this point, it's at the point where D is 0. So the Q has got to be 0 for that duration. But when D changes to 1, for this moment, Q output will be 1 as well. Alright, because when the gates open, the Q output will reflect whatever's on the data input. Just have a look at that anyway. It'll pay you some dividends later on. Right. I'll probably leave things here, but before I go, I'm giving you this very simple circuit, and you might have seen something very similar in topic 2. I've got two AND gates, and I've got a NOT operator here, which just inverts the value of whatever's being input. So supposing D is 1, and supposing E or G, the gate, is 1, then that's going to be 1. And this input to this second AND gate is going to be 1. This is 1 here, but then its value is going to be inverted, so you get a 0 here. And since this is an AND gate, I'm going to get a 0 here. But this is going to be 1. And this device is called an SR flip-flop. It's a set reset flip-flop, and what it means is that if you set it, the Q output is going to be 1. So if you put a 1 here, I'm telling the device to set the value Q to 1, and this will actually be 0 because I'm inverting the value of Q. Look, there's a little circle here. It means not whatever Q was, and that's 0. On the other hand, if D is 0, then this is going to be 0, and as a result of this input being 0, this output is going to be 0. So I'm not going to do a reset, but this line is going to be 0, and it's inverted, so it's not 0, which is 1. So this input of the AND gate is going to be 1. If the gate or E is 1, that second input is going to be 1. And hence, the reset pin is going to be activated. And what the device does, because it's an SR device, set reset device, is that uh, Q is going to become 0. It's going to have a 0 there, reset value. It's going to be in the reset state. And not Q will be output on this line, which is 1. So not Q. This is not Q. So I can actually explode the RS flip-flop to look inside it. This is what it looks like. And the only thing I want you to notice at the moment is that the RS flip-flop, this system here, has got some logic gates inside, but it's also got some feedback. So the output of this NOR gate is going to be fed back into this NOR gate. Okay, and I want you to just notice that, and the definition of a state machine, such as this very simple RS flip-flop, is that it will be implemented by means of the presence of feedback. And I'll leave it at that, apart from saying, well, let's have a look at, let's just go back to look at the generic Moore machine. And what do you notice here? What did I say it's got? It has feedback. And feedback, the presence of feedback, is essential for a machine whose operation works on the basis of changing from current state and current inputs to next state. So in the case of the RS flip-flop, if you input a 1 and maybe one of the inputs is a gate, then you're going to end up outputting a 1 here. On the other hand, if you've got an input of 0 and the gate's on and you're in a particular state, which is, that's supposing it's the state 1, you've got a 1 here, then your new next state is going to be 0 and you're going to output a 0. Okay, so I'll leave you to have a little bit of a think about that. I've given you a lot of ideas that you may not have come across before, so there's a bit of a challenge in that. And little exercise for you to do is to look at the diagram here and a little test of your understanding. If D is 1 and you set G to be N and these are all 1s, just make sure that you can calculate that Q is 1. Q is 1. If G, the gate changes to 0, then Q will actually stay at 1. Stay at 1. If the input is 1. If G is 1. Okay. If the gate changes to 0, Q stays at 1. In other words, it remembers the value that was on the input N. And have a look at that maybe. Okay, that's a Mealy machine, so that's a slightly other thing. Okay. So I end up this discussion by showing you a machine where you've got the data input here as before, data input D as before, you've got the Q output as before, and the gate is now being replaced by a clock signal. So the clock signal is very symmetric. It's 0, then it goes after a fixed period to 1 and stays at 1 for a fixed period, and then goes to 0 after a fixed period and then stays at zero for a fixed period, and so on. So you can think of this, whatever digital value is on D, when you get the clock coming in, going to 1, you're going to change S to whatever value is on the input. So you can what I suppose sample the value, the digital value on in very very rapidly and reflect its outputs on out. But we'll talk about this much later on in the course. But I just wanted to show you that this little device here actually corresponds to uh, my version of the generic Mealy machine, which I've got here. And you see I've got a little bit of memory here, and I've got a clock going into memory. So it's like the enable pin or the gates going on and off, on and off. And the significance of memory being clocked in this way is that every tick of the clock I'm going to uh, calculate a new next state, and that's going to be fed back. And the next tick of the clock, given these inputs and this state, I can calculate what state the machine's going into. Okay, so hopefully most of this makes good sense, and with a bit of your study of it, it's going to make a lot more sense, and you'll see what I'm doing. What we've been preoccupied with doing here is just to look at the notion of a 1-bit memory storage as being a two-state finite state machine. And if we understand state machines, we can very easily make the transition to building much more complicated machines, like vending machines, or computing devices, or whole computers, as complicated finite state machines. So anyway, thanks very much for listening.